Good morning, students. Yes. So, last class we were discussing about P block elements, right? So we had completed group 13. Group 13, then we had started with the synopsis for group 14. So we had reached allotropes. Okay, we'll continue from that, from allotropes. So what are allotropes? Allotropes are different physical forms, okay, of the same element which are having same chemical properties, but their physical forms are different or their physical properties are different. So then it is said to be allotropes. So what are the different allotropes of carbon? Diamond, graphite, fullerene. Okay, so the nanotube, carbon nanotube. Okay, so these are some of the allotropes of carbon. Okay, allotropes means what? They are having different physical forms and they are having same chemical properties. Okay, so what are the three main allotropes of carbon? So diamond, graphite, and fullerene. So we will be discussing about these three allotropes. So these are the structures of graphite, diamond, and fullerene. Okay, you can see these are the structures, how they are represented. So how is diamond? So diamond is a allotrope of carbon. So it is extremely hard. It is having high reflective crystalline form of carbon that is usually colorless, and it is used as gemstone and in abrasives, cutting tools, and other applications. Okay, you know diamond is hard. Okay, it is having a higher refractive index. It is colorless. It is used in gemstones. Okay, it is used as cutting tools and other applications. So what is the structure of diamond? So the diamond, you can see the structure. So the electronic arrangement of 2 and 4 carbon. So it is what? In this, each carbon atom shares electrons with the other 4 carbon atoms, forming 4 single bonds. So you can see the structure, right? So you can see here, so each carbon atom is again linked to other 4 carbon atoms, forming a 4 sigma bond. So these are the different sigma bonds. So like this, they form the diamond structure. So it is like this. Okay, so this is a structure of diamond. So what are the properties of diamond? So it is a high melting point. It has high melting point. It is extremely hard. Extremely hard means it is difficult to break. So there is no electrical conductivity. Why? Because the electrons are localized in specific bonds. So there are no free electrons. If there are free electrons, then there will be conductivity, right? So there are no free electrons. So no free electrons means no electrical conductivity. So these are insoluble in polar as well as non-polar solvent. Why? Because of the molecular bonds, because the bonds, that is sigma bonds, are stronger than any intermolecular forces. Okay, so here because of the molecular bonds that are stronger, so they are insoluble in polar as well as non-polar solvents. So next is graphite. So graphite, you know, graphite, it is used in pencils, right? So it is lead pencils. So it is a soft crystalline allotrope of carbon, which is composed of graphene layers. Okay, so these graphite, it is made up of layers. So they have having graphene layers, having a steel gray color, right? Steel gray to black color. It is having a metallic luster and a greasy feel. Okay, so where it is used in lead pencils, lubricants, paints, etc. So these are the application where you can use your graphite. Okay, so what is the structure? So here what happens, so you know, it is allotrope of carbon, right? So here the each carbon atom is covalently bonded to other 3 carbon atoms. Okay, so in case of diamond, how it was, 1 carbon atom has been linked to other 4 carbon atoms, right? But in graphite, 1 carbon atom is covalently bonded to other 3 carbon atoms. So here graphite consists of layers of carbon atoms. So here the graphite, how it is, the sheets are there. Okay, graphite sheets, they are having layers. So layers of carbon atoms are there. Okay, so it is having a layer structure, and it is very difficult to draw the structure. Okay, it is very difficult to draw the structure. So you can see here below, right? You can see the below. So this is the arrangement of atoms in each layer. Okay, so this is the, how it is spaced. So here, how is the structure? That is, each carbon atom is linked covalently to other 3 carbon atoms. Okay. Unlike in diamond, it is each carbon atoms is attached to other 4 carbon atoms. So this is a structure of graphite. So what are the properties of graphite? It is having high melting point. Okay. It is having a soft, it is slippery feel. Okay. Where it is used in pencils, it is used as a dry lubricant, okay, for things like clocks. Then it has lower density. So as compared to diamond, your graphite has having a lower density, okay, lower density. So it conducts electricity. Why? How it conducts electricity? Because in case of carbon, okay, in case of your diamond, so each carbon atom has been linked to other 4 carbon atom, but here each carbon atom is linked to other 3 carbon atoms. So there is 1 electron which is free. Okay, it is free. So it is moving, right? So it is the delocalized electrons here. They are free to move throughout the sheet. So there is a delocalized electron is present. Okay, 1 electron is present, electron. So that is delocalized. So thus it can conduct electricity. So it is insoluble in water and organic solvent. So next is fullerene. So why the name fullerene was given? So it is a carbon. It is a pure carbon molecule which consists of C60 carbon atoms. Okay, it is called as C60. So it is a carbon that is a fullerene is made up of carbon 60 atoms of carbon. Okay, so this fullerene has a shape similar to saucer ball. Okay, it is having the, you can see the diagram here, right? So it is having the what shape similar to that of saucer ball. Okay, and it is referred to as the bulky ball. Okay, so it is referred as bulky ball. So what is the structure of fullerene here? So they consist of hexagonal rings. So you can see here, you can see the structure here, right? So it is consists of hexagonal ring, right? So here, see here, hexagonal rings are there. Okay, so these are hexagonal rings. So like this, the hexagonal rings of carbon atoms, okay, they are alternatively, they are there, and alternatively there are pentagonal rings also. So alternatively hexagonal and pentagonal rings are there, which allows the curvature of the surface. Okay. So here the carbon-carbon bonds in Buckminster fullerene forms a pattern like saucer ball. So like this, alternatively there will be hexagonal and pentagonal, pentagonal. So alternatively, there will be hexagonal and pentagonal. So this together it makes a shape of a saucer ball. Okay. So your fullerene is a brownish reddish magenta color. Okay, which when dissolved in organic solvent. So why it is called as Buckminster fullerene? Because it has a geodermis shape. Okay, it has a geodermis shape like the saucer ball. Okay, so we'll go for the next. So what are the properties of fullerene? So the molecule can act as semiconductor, conductor, and superconductor under specific condition. So it displays photochromic effect. Means what? It can change in light transmission based on intensity. So there will be changes in light. Okay, photochromic effect means what? So light, the intensity can be changed. Okay, so the display. So the display of the photo intensity can be changed. So this is insoluble in polar solvents, and they are sparingly soluble. That is not completely soluble nor incomplete. Okay, so they are sparingly soluble in alkanes. These fullerenes are relatively safe and inert, and yet they have properties that allow the substance to create active derivatives. Okay. So, so we'll see some of the compounds. So first compound of carbon is carbon monoxide. So how carbon monoxide is formed? That is, it is a combination. It is direct combination of compound carbon in limited supply of air or oxygen. Okay, gives you carbon monoxide. So you can see here carbon. So directly carbon, it is treated with your this what you are supplying your oxygen. Okay, it gives you carbon monoxide. So these are the different various laboratory method. Okay, if you take formic acid, and you treat it with H2SO4, okay, at 373 Kelvin, it gives you carbon monoxide, which is pure. Okay, so like this, it is a laboratory method. Then on commercial scale, okay, commercial scale, you can produce your carbon monoxide by heating, okay, by passing a steam, okay, by passing steam over coke. This so this is a reaction which you can see. So coke, when you when you pass your steam on coke, okay, at 473 to 1273 Kelvin, you get water gas. So this is water gas. CO plus H2 is called as water gas. So like this, you can get your carbon monoxide. Okay, so this is the commercial method. So commercial method means what? You can produce your carbon monoxide at a large scale. Laboratory method means in laboratory at a very small scale you can produce. Okay, then one more method, when air is used instead of steam. So here we have used steam. So if you use air, okay, air consists of different ingredients, like so it constitutes of different particles. So here instead of steam, if you pass air, so a mixture of carbon monoxide and N2 is produced. So this is called as producer gas. So remember, what is water gas? Carbon monoxide plus H2. Okay, what is producer gas? Carbon monoxide plus N2. How you obtain it? When you pass steam, instead of steam, if you pass air, okay, air consists of nitrogen. So air, okay, air consists of nitrogen, oxygen, right? So your coke, so when you pass your oxygen, nitrogen, okay, that is air, on this coke, over the coke, you at 1273 Kelvin, you get carbon monoxide plus N2. This is called as producer gas. Very important, remember this. Okay, so what are the properties? So you know the chemical formula is CO, the appearance, it is colorless, it is odorless, it is soluble in organic solvents, okay, it is powerful reducing agents, okay, and it reduces almost all metal oxides, then the alkali and alkaline earth metals. So it is used in extractions of many metals from their oxides. So these are some of the properties of carbon monoxides. Next, we'll see carbon dioxide. So how it is prepared? So it is prepared by complete combustion. Okay, it is prepared by complete combustion of carbon and carbon containing fuels in excess of air. Okay, so carbon plus oxygen, O2, when you heat it, you get carbon dioxide or methane. Okay, methane, it is a hydrocarbon. So when you do a complete combustion, that is methane plus O2, oxygen. When you when you do complete combustion with methane, you get carbon dioxide, carbon dioxide, okay, and plus water molecule. So and in laboratory, how it is so how you can prepare it in laboratory? If you treat it by calcium carbonate, okay, if you treat your calcium carbonate with dilute sulfuric acid, dilute chloric acid, okay, hydrochloric acid, you get calcium chloride plus CO2 plus water. So this is a laboratory method, means what? You can produce your carbon dioxide at a very small scale. Okay, next is commercial method, that is how you can prepare it at a large scale. So it is obtained by heating calcium carbonate. Okay, calcium carbonate at 1600 Kelvin, you get calcium oxide plus CO2. So like this, you can obtain it in a commercial scale. So if you do a fermentation, if you do fermentation, okay, of so it is a manufacture of ethyl alcohol. So it is a valuable byproduct in the manufacture of ethyl alcohol by fermentation of glucose and fructose. So if you do a fermentation on glucose or fructose, the enzyme used here is zymase. Okay, zymase is the enzyme. So you yield what? You yield ethyl alcohol and carbon dioxide. So in the manufacture of ethyl alcohol also, by fermentation method, you can obtain your carbon dioxide at a very large scale. So what are the properties of carbon dioxide? So they are colorless. Okay, it is sweet smelling smell, that is non-toxic in low concentrations. It is more dense than air. Okay, it will not undergo thermal decomposition and inability to support combustion. So because of this property, they are used in fire extinguishers. Okay, they are used as fire extinguishers. They are pure. They are having poor solubility in water. Okay, it sublimes. Sublimes means what? It does not enter into the liquid state. Directly from solid, it turns into vapor state. Okay, so the example is dry ice. Okay, the carbon dioxide, it is called as, what is dry ice? Is solid carbon dioxide. So it sublimes. Sublime means what? Directly from solid, it goes into vapor state. Okay. So these are some of the properties of carbon dioxide. So next we'll see some of the compounds of silicon. So silicon being the second member of group 14 has much larger size, okay, and lower electronegativity than that of carbon. So we'll see some of the compounds of silicon. First is silicon dioxide. So silicon dioxide is also known as silica, okay. So 95% of the Earth's crust is made up of silica and silicates, right? So it is a three-dimensional network. So it is a three-dimensional network solid in which silicon atom is covalently bonded in a tetrahedral manner to four oxygen atoms. Okay. So this is the structure of silicon dioxide. So you can see here. Okay, silicon dioxide is silicon atom is attached to four other oxygen atoms. So like this, it is the structure of Yes, students, sorry, there was some network issue. Are you able to see the screen now? Are you able to hear me? Yes, thank you. Okay, we'll continue. So this is the structure of silicon dioxide. Okay, so we'll go for the next one. So silicon, so this is silicon tetrachloride. So silicon tetrachloride is another compound of silicon. Okay, so how it is prepared? It is prepared by action of chlorine on silicon. So this is a preparation. Okay, so this is a preparation of silicon tetrachloride. So silicones. Okay, silicones is also one of the another compound of silica. Okay, that is silica. So here silicones are polymer that include any inert synthetic compound made up of repeating units of siloxane. Okay, siloxane. So this is silicones is very important. So it is a chain of alternative silicon atoms and oxygen atoms. Okay, which frequently combined with carbon or hydrogen. So silicones is very important. So how it is? So the structure is made up of repeating unit of siloxane. Okay, siloxane. Siloxane means what? The chain consists of silicon atoms and oxygen atoms. Okay, frequently, and it is combined with carbon and or hydrogen. So you can see. So the where are these the uses of silicones? So soup ladle and pastel ladle. Okay, which is made up of silicones. Then the food steamer to be placed inside a pot of boiling. So these are some of the uses of silicones. Silicates. Okay, silicates is also another compound of silicon. So it is a compound containing of anionic silicon compound. Okay, so here the for this is so the majority of silicates are oxides. Okay, oxides, but hexafluorosilicates and other anions are also included. So orthosilicate is the anion. Okay, that is SiO4 4 minus. How it is represented is SiO4 4 minus. So it is related to orthosilicates. So orthosilicates, they are nothing but they are the families of anions. Okay, anions means what? With negative charges, right? So the formula of this compounds, okay, or that is the, in general, it is given by SiO2 plus N plus 2 in the bracket close to raised to 2N minus. Okay, so this is the silicates is also important compound of silicon. So where are the uses? What are the uses of silicates? So it is mainly used in detergents, papers, water treatment, and construction materials. Okay. So this is the silicon tetrachloride, right? We had seen silicon tetrachloride. So this is a silicon tetrachloride. So this is silicate. You can see here. So this is the structure of silicates. Okay. This is a structure of silicates. So what are zeolites? So zeolites is also an important concept. So these are micropolar polars, okay, aluminosilicates, minerals which are commonly used for commercial absorbents and catalysts. Okay, zeolites. So these zeolites, they have micropores. They have micropores. So these are naturally but also produced industrially. So these occur naturally. Also, they are produced industrially on a large scale. Okay, so zeolites, so these are aminosilicates minerals. Okay, so these are aminosilicates minerals. So where it is used as absorbents and catalysts. So what are the uses? So they are widely used as ion exchange beds in domestic and commercial waters, purifications, softening, and other applications. Okay, so zeolites are used to separate molecules. Separate molecules, how it can be used to separate molecule based upon their sizes and shapes. Okay, based upon their sizes and shape, you can separate using this zeolites. Okay, so these are some of the uh, concepts, okay, of group 14. So based on this, we'll solve some questions now. So which of the following is a conductor of electricity? Yes. Which of the following is a conductor of electricity? Yes, it is graphite. Why it is graphite? Because it has a delocalized electron, right? It has a delocalized electron. So because of the reason, so it is a good conductor of electricity. So we'll go for the next. Diamond is harder than graphite because what is the reason why diamond is harder than graphite? Why diamond is harder than graphite? Graphite is planar, diamond has free electrons. Okay, diamond is sp3 hybridized. So the reason is D. Okay, D is the reason. Graphite is sp2 hybridized. So C is also wrong. Diamond has free electrons. No, graphite is planar. This is not the reason why diamond is harder. Okay, so the answer is none of above because diamond is harder than graphite. Okay, it is due to the three-dimensional packed structure of carbon atoms. Okay, so because of this reason, diamond is sp3 hybridized, and it has a three-dimensional packed structure of carbon atoms. So this is the reason why diamond is harder. So the answer is none of the above. Okay, it is D. It is D. In graphite, the sheets are held by, how the sheets are held in graphite? Yes, it is Virat. Yes, it is weak van der Waals forces. Okay, it is weak van der Waals forces. So it is C. Okay, C is the correct answer. So we'll go for the next one. Poisonous gas present in exhaust fumes of car is. So which is a poisonous gas which is present in the exhaust fumes of car? So it is. So the gas, poisonous gas which is present, okay, in the exhaust fumes of car is carbon monoxide. It is C. Okay, it is carbon monoxide. So why carbon monoxide? How carbon monoxide is formed? It is formed by incomplete combustion of fuel, right? It is formed in incomplete combustion. So the answer is carbon monoxide. Living in the atmosphere of carbon monoxide is dangerous because of it. What is the reason why living in atmosphere of carbon monoxide is dangerous? What is the reason? If in atmosphere carbon monoxide is present, why it is dangerous for living beings or for living purpose? Yes. Right, Lohit Kumar, it is C. It because the reason is it combines with hemoglobins of blood and make it incapable to absorb oxygen, right? So this is the correct answer. So we'll go for the next. Carbon monoxide combines with hydrogen when heated to 150 to 160 degrees Celsius in the presence of catalyst to give A. Acetaldehyde, B. Methyl alcohol, C. Acetone, D. Formaldehyde. So what is the reason how carbon monoxide combines with hydrogen? What does it produce? Yes. So the reaction takes place as follow: carbon monoxide plus H2. Okay. At 150 to 160 degrees Celsius, it gives methanol. It gives what? It gives methanol. Okay. So the answer is methyl alcohol. Okay. That is B is the right answer. Understood? So we'll go for the next one. Carbon monoxide is not. So carbon monoxide is not a what? Good oxidizing agent, a reducing agent, neutral to litmus, poisonous in nature. So what is the answer? Why carbon monoxide is not a, yes, it is not a good oxidizing agent. Okay, it is used as a reducing agent. Okay, it is used as a reducing agent in metallurgy. That is, okay, it is used as a good reducing agent, not a oxidizing agent. So A is the correct answer. LPG. LPG contains mainly, what does LPG contains? What does LPG contains? Yes, LPG contains what? Yes, Lohit Kumar, it is C, that is butane and propane. So it consists of butane and propane. Yes. Okay. So we'll go for the next one. Producer gas is a mixture of. Yes, we had discussed this. What is producer gas? What is producer gas? What is producer gas? Yes, producer gas. It is carbon. A is the correct answer. Okay, carbon monoxide plus N2, right? Carbon monoxide plus N2, right? So this is the correct answer. So we go for the next one. Phosgene is, phosgene is, what is the formula of phosgene? What is the formula of phosgene? Yes, it is D. Yes, D is the right answer. Most of you have answered it right. It is D, right? So D is the right answer. Okay. So the answer is D. Okay. Which oxidation state is not shown by carbon in its compound? So which is the oxidation state which is not shown by carbon in its compound? So which oxidation state is not shown by carbon in its compounds? It is, okay, it is B. Okay, it is B is the answer. Okay, B is the answer. See, carbon in ground state, it will have oxidation state of 0, +4 or -4. So in ground state, carbon can have 0, +4 or -4. Okay, to attain stability, so it attains stability by gaining octet or duplet configuration. Okay, but it will be unstable at +1 configuration. So it can show 0, +4, plus minus. So to show +1 oxidation state, it will be unstable. So it will be unstable. So it shows the oxidation state which is not shown by carbon is +1. So +1 is the answer. Okay. So we'll go for the next one. Which of the following elements does not show allotropy? Which of the elements which does not show allotropy? Which element does not show allotropy? Yes. Which is the element which does not show allotropy? Carbon, silicon, tin, or Pb? So it is lead. Okay, D is the answer. Lead is the answer. So all the element except lead, okay, it of the 14th group shows allotropy. All others they show allotropy. form, and they have allotropic form. So, but lead, okay, lead does not show allotropy. So D is the answer. So D is the answer. So we'll go for the next one. Which of the following oxidation state are the most characteristic for lead and tin respectively? Yes. Which is the oxidation state shown by lead and tin respectively? Yes, +2 +2 +4 +2 +2 +4 +4 +2 +4. So we had discussed about oxidation state. As you go down the group, what will happen? What will be? There will be increase in inert pair effect, right? We had discussed this in group 13. So there will be increase in inert pair effect. So inert pair effect means what? Intervening of D and F electrons, right? So there will be interference of D and F electrons, right? So because of that, what happens? So the tendency to lose electrons will increase, right? So because of this, so as you go down the group, due to the increase in the inert pair effect, tendency to lose only 2 electrons increases, right? So as you go down, so because of this reason, what it will show oxidation state, it will show +2. It will show +2. Okay. So it shows +2. So tin and lead, they show +2 oxidation state. See, plus most of you have answered is +2 and +4. So this is +2 and +4 is fine. Okay, but due to interference, okay, due to interference of D and F orbitals, okay, what happens? So the most stably, okay, most stable oxidation state which it can show is +2 and +2. Okay, it will show +2 and +4, but most stable, okay, most stable oxidation state is +2 and +2. Okay, so the to lose the 2 electrons as you go down the group, it will be, it will increase the affinity will be more to lose 2 electrons. Okay, so it will be +2 and +2. So it will show characteristic +2. Okay. Lead shows oxidation states of, lead shows oxidation state. What is oxidation state shown by lead? Yes, it is C, +2 and +4. Yes, right. Right answer. Density is highest for. Density is highest for. Density is highest for. When you talk about density, how do you talk about density? Density is mass per unit volume, right? So as you go down the group, what will happen to atomic mass? Atomic mass goes on increasing. Okay, so how do you place the this carbon, silicon, germanium, tin and lead? So which is at the bottom? Lead. Yes, Rakshita, it is a D. Okay, it is D. So lead, sorry, it is C. Okay, C is the answer, that is lead. So lead, why? Because carbon, silicon, germanium, tin, and lead. Okay, you know density is what? Density is mass per unit, right? Mass per unit volume. So as you go down the group, what will happen to atomic mass? Atomic mass increases. So density of lead will be more. Understood? So we'll go for the next one. Which of the following is a semiconductor? So carbon, lead, germanium, and tin. Okay, which of this among this is semiconductor? Yes, it is germanium. Okay, it is germanium. So as you go down the group, what will happen to metallic character? Metallic character will increase. Okay, therefore, what will happen to conductivity? So conductivity also increases. Okay, conductivity also increases. Okay, so germanium is a semiconductor. Silicon is diagonally related to. So silicon is related to what? Silicon is related to what? Diagonally means what? Like this. So silicon is here, right? Carbon, silicon. So diagonally it is related to what? Yes, it is related to boron. So C is the answer. Okay, so boron is the first element of group 13 and silicon is the second element of the group 14. So because of this, so these are diagonally related to each other. Okay, so this is the boron. So correct, boron is the right answer. So next is group 14. Okay, group 14, we have completed group 13, group 14. So next is group 15. Okay, so what is group 15? So group 15, they are nitrogen compounds. Okay, nitrogen family. So nitrogen family, what is the electronic configuration? It is NS2, NP3. So which are the elements of group 15? It is nitrogen, phosphorus, arsenic, antimoney, bismuth. Okay, so these are the elements present in group 15. Okay, so what is the electronic configuration? It is NS2, NP3. So these are the elements. So their symbol, the atomic number, their electronic configuration. Okay, so these are the electronic configuration of the nitrogen family elements. Okay, so we'll go for the next. So what is the trend? Okay, what are the periodic trends it follows? So what about electronegativity? So electronegativity, it decreases down the group. Okay, around the group 15. So when you're talking about group 15, so the electronegativity, it decreases down the group. What about ionization enthalpy? Ionization enthalpy also decreases down the group. Okay, why it decreases down the group? Why it decreases down the group? Ionization enthalpy. As you go down the group, what will happen to atomic size? It goes on increasing, right? It goes on increases. So therefore, what happens? The amount of energy which is required to remove the last electron, okay, it goes on. So it will be more, right? So as you go down the group, it will go on becoming less. So as you go down the group, so there will be shielding effect. So there will be screening effect. So the electron and the outermost electron will be far away. So you can easily remove the outermost this electron, right? So because of this reason, it goes on decreasing. Okay. Then atomic radii goes on increasing. So increases as you go down the group, the atomic size goes on increasing as there is addition of new subshell, right? So because of this reason, it increases. So atomic radius, it increases down the group. Next, electron affinity. What is electron affinity? It is the ability of an atom to accept an electron. So this also goes on decreasing down the group. Melting point. So melting point, as you go down the group, it increases. Why? As you go down the group, what will happen? The atomic size goes on increasing. So this is the reason it increases going down the group. Boiling point also, it goes on increases as you go down the group. Okay. So these are some of the periodic trends seen in group 15. So what are the different allotropes of the group 15? So nitrogen, alpha nitrogen, which is cubic structure, and beta nitrogen, which is hexagonal crystalline. Phosphorus, the allotropes are white phosphorus, red phosphorus, black phosphorus. Arsenic, yellow, black, and gray metallic. Okay. Then antimony, it has yellow form, metallic, and explosive. So these are some of the allotropes. Bismuth, they do not have allotropes. Okay. So what are the different chemical properties? So these are the different reactions shown by group 14. Okay. So it acts as an oxidizing agent. So you can see the different reactions. So action of air. Okay. So nitrogen plus oxygen, it forms a nitric oxide. So these are it acts acting as an oxidizing agent. Okay, so these are the different reactions. So hydrides. So all the group 14, okay, group 15, they form hydrides with the formula EH3. Okay, EH3, where E is different elements of group 15. Okay, that is nitrogen, phosphorus, antimony, bismuth, arsenic, etc. Okay, so the oxidation state is -3 here. So hydrogen bonding is present in ammonia, right? Hydrogen bonding is present in ammonia. So the stability of hydride, it goes on decreases as you go down the group because of due to the bond dissociation energy. So as you go down the group, what will happen to bond dissociation energy? Bond dissociation energy means what? The energy which is required to break the bond. So the energy required to break the bond goes on decreasing. So because of this reason, the stability of formation of hydride goes on decreasing. Okay. So what are the anomalous properties? Okay, how the nitrogen is, that is the first element is nitrogen, how it is acting different from other elements. So it is nitrogen is gas, all the others are solids. Okay, nitrogen is diatomic and other elements are tetraatomic. It forms hydrogen bonds in hydrides. Okay, and others they form pi bonding. Okay, it forms pi multiple bonding. That is pi electrons are, that is from p orbitals, the pi electrons are forming the bond formation. So it undergoes a multiple bond system. So the range of oxidation state is from -3 to +5. So as nitrogen, they do not have d orbitals, right? It is the first element of the group 15. So they do not have d orbitals. So it does not form any coordination compounds. So so what is the lab method? So lab method of preparation of dinitrogen, it is from ammonium chloride plus sodium nitrate. Okay, when you treat this, you get dinitrogen plus H2O plus NaCl. So this is a laboratory method. From azide, that is sodium azide, you get sodium plus N2. So this is another method, laboratory method. So these are the different chemical reactions, okay, chemical properties. So preparation of ammonia. Okay, ammonia, it is prepared by heating a mixture of calcium hydroxide and ammonium chloride. So this is a reaction. Okay, so like this. So one more, the important method of preparation of ammonia on a large scale, it is Hebber's process. So this is a Hebber's process. So what is Hebber's process? You are reacting your nitrogen and hydrogen, okay, in the presence of finely divided catalyst. So which is the catalyst used here? It is aluminum oxide, ferric oxide, and potassium oxide. So this is a catalyst which is taken in finely divided manner. Okay, and the temperature provided is 700 degrees Celsius, and the pressure is of 200 atmosphere. Okay, so this reaction is reversible. Reversible means what? So it can, the products can undergo back reaction to give you the reactants. Okay, but here complete, it is not possible to convert all the reactants into ammonia. Okay, so to separate now, how if once your product ammonia is formed, how you can separate the ammonia from the mixture is that you have to cool it. Okay, you have to cool it, and then the ammonia, what will happen? It will liquefy and it will be separated. Okay, so the uncombined, if there is some uncombined nitrogen which is not combined with hydrogen, so it is again recycled. Okay, so it is recycled, or another way is that it can be separated by passing the mixture into water. So after passing the mixture into water, only the ammonia which is left, it will be dissolved, okay, in the water. So this is Hebber's process, important reaction, and the reaction conditions. So this is the Hebber's process. Remember what is the catalyst used and what is the reaction conditions. So this is the structure of ammonia. Okay, it is a trigonal pyramidal structure. So ammonia, as it has a lone pairs of electrons, what will happen? So there will be lone pair, bond pair repulsion will be there. So because of this structure, okay, instead of a tetrahedral angle, it will undergo a bit, the angle will be less. Okay, it has 107.8 degree. So because of the presence of lone pairs on nitrogen. So this is the structure of ammonia. So next is nitric acid. Okay, how do you prepare? Lab method is by preparing sodium nitrate plus H2SO4, giving you nitric acid. Okay, then large scale. So these are the various preparations of nitric acid. Okay, so you can just go through the reactions. So large scale, ammonia plus oxygen. Okay, ammonia, when you treat it with oxygen, so what is happening? You get nitric oxide plus H2O. So nitric oxide is then reacted with oxygen in air to form nitrogen dioxide. Okay, so like this is a large scale method. Okay, then again, whatever the nitric oxide is formed here. So nitrogen dioxide is formed. It is reacted with water to give you this what HNO3. Okay, so this is the method that is in large scale method. Large scale. So this is the preparation. Okay, this is the preparation. Okay, this is the preparation methods. So this is a structure of nitric acid. So you can see this is the structure of nitric acid. Okay, so this is a structure of nitric acid. So these are some of the chemical properties. So phosphorus. So we have seen phosphorus. It exists in 3 allotropic forms, that is red, white, and black phosphorus. Okay. So white phosphorus, when it is burned, when you burn it in air, okay, it gives you a faint green glow. So this is called as chemiluminescence. Okay, it is called as chemiluminescence. So phosphine. So another method of preparation of phosphine. So this is another compound of phosphorus that is called as phosphine. So the preparation, see the phosphine preparation from calcium phosphide. Okay, calcium phosphide, when you react it with water, you get phosphine. Okay, so this is the method of preparation of phosphine. Then next is phosphorus trichloride. Okay, next is phosphorus trichloride. So how do you obtain phosphorus trichloride? When you pass a dry chlorine over a white phosphorus, you get phosphorus trichloride. You get phosphorus trichloride. Okay, so it is also obtained by action of thionyl chloride with white phosphorus. So these are some of the reactions. So this is the structure of PCl3 and this is the structure of phosphorus pentachloride. Okay, so we'll solve some questions based on this. So nitrogen combines with metals to form. So what does, when nitrogen it combines with metals, so it forms what? What it forms? Yes, it forms nitrides. Okay, it forms nitrides. So it forms nitrides. Okay, it is D. The answer is D. So that is, for example, Mg. If I take Mg plus N2, gives you Mg3N2. Okay, this is the nitrite. So nitrogen, when it reacts with metals like lithium, magnesium, it gives you nitrite. So this is the answer. D is the answer. Laughing gas is prepared by heating. How is laughing gas prepared? How is laughing gas prepared? So laughing gas is prepared by, yes, how is laughing gas prepared? It is prepared by treating your ammonium chloride with sodium nitrate. Okay, remember this. It is prepared by treating your ammonium chloride with sodium nitrate. So laughing gas is N2O. It is N2O. So this is laughing gas. Okay, dinitrogen oxide. Okay, so when this is prepared, how? It is dinitrogen oxide. It is called as what? It is dinitrogen oxide. So dinitrogen oxide. So when you treat ammonium chloride with NaNO2, okay, it gives you 2N2O plus 4H2O plus 2NaCl. So this is the reaction. So it will be 2NaCl, 2NaNO3. Okay, so like this is the reaction. So remember this, laughing gas is prepared with ammonium chloride and sodium nitrate. Okay, so we'll go for the next one. Catalytic oxidation of ammonia gives. Catalytic oxidation of ammonia gives. Catalytic oxidation means what? Oswald process. Okay, Oswald process. 4NH3 plus SO2 gives you 4NO plus H2O. So this is Oswald process. So what it obtains, you get nitric oxide. Okay. So catalytic oxidation of ammonia means it is a Oswald's process. It forms nitric oxide. Okay. So it is B. Yes, B is the answer. So we'll go for the next one. Which of the following has highest dipole moment? So which of the following is having highest dipole moment? Highest dipole moment means what? Dipole moment means what? When you have a polar system. Okay. So here, which will have highest dipole moment? These are the following are the molecules. So which will have highest dipole moment? Yes, A. Okay, ammonia will have highest dipole moment. What is the reason? What is the reason? So ammonia, so this will add up, right? All the dipole moment. So nitrogen is more electronegative, so it will add up to give you a resultant vector in the state direction. So okay, so it will give you, so ammonia has highest dipole moment, which is due to high electronegativity of nitrogen. Okay, due to which charge on nitrogen and this hydrogen. Okay, so because so all the charges will be added up on nitrogen, and thus so the dipole moment will be more. So the answer is A. A is the answer. When concentrated HNO3 is heated with P2O5, it forms. Okay, we'll write the reaction. So that is when 2HNO3, okay, it reacts with P2O5. What it gives you? It gives you 2HPO3 plus N2O5. Okay, it gives you HPO3 plus N2O5. So the answer is D. Okay, remember this. So when concentrated HNO3 is treated with P2O5, it gives you D is the answer. In Haber's process for the manufacture of ammonia, the catalyst used is which is a catalyst used? Which is a catalyst used? Ferric oxide, ammonium oxide, and potassium oxide, right? It is C, right? It is C. It is finely divided iron. Okay. So in the Haber's process, manufacture finely divided is used. Okay. Iron is used. Amylase behavior of nitrogen is due to. Yes. Why nitrogen is showing different behavior than other elements? Why it is having a different behavior than other? What is the reason? Because of small size and high electronegativity, non-availability of d orbitals, easy bond formation. Yes. 39th, what is the answer? It is D. Yes. D is the answer, all of the above. So these are the reasons why nitrogen is showing anomalous behavior due to small size and high electronegativity, non-availability of d orbitals in valence shell, and ease of multiple bond formation. Okay. So these are the reason. Okay. D is the reason. So, nitrogen, it is the first element. So there will be no d orbitals also, right? So, the small size, it is a small size. First electron, first element means it is high electronegativity also. Okay, so the answer is D. D is the answer. So, so we'll see group 16, 17 and 18 in the next class. Okay. And I'll solve some of the last year questions also in the next class. Okay. Most of you have asked me to solve last year's paper, questions on this chapter. So I'll be solving it in the next class. Okay. So we'll stop it for today and we'll continue in the next class. Thank you.